Hi everyone, I'm Sleepless Scientist. Tonight we're staring into the dark side of the universe. Not the villainous kind, not exactly, but the kind that mirrors everything you've ever known, and yet could erase you in an instant. Tonight we're exploring a substance so elusive, so elegant, and so explosively misunderstood that it sounds more like something from science fiction than science class antimatter. But don't worry, there's no pop quiz, no charts, and no physics degree required. Just a quiet space, a sleepy mind, and a strange little question hanging in the air. Why does antimatter exist? And why are you made of matter? Instead, I'd love to know where in the world you're listening from and what time it is for you. Let me know in the comments below. I'm always curious where these quiet little science stories are drifting to, and if this video helped you while you were there. Now relax, take a deep breath, and join me gently on this evening's journey. You shuffle under the sheets, roll onto your side, and stare at the ceiling. Antimatter. Sounds like something a moody superhero might throw across a room. But it's not some comic book magic, it's real. Stranger still, it's kind of the twin of everything around you. Every particle you know, electrons, protons, neutrons, has an equal and opposite sibling, an antiparticle. Same mass, same spin, but the electric charge is flipped. If an electron is 1, a positron is +1. That's not poetry, it's particle physics. And here's the kicker. If one of these twins meets its counterpart, boom. Instant annihilation. Not metaphorically. They vanish like shy ghosts, leaving only a flash of pure energy behind. Scientists call it mutual annihilation. You might call it the most awkward first date in the universe. Oddly enough, that energy isn't some mythical force, it's governed by Einstein's famous equation, A equals mc2. The m here is the mass of the two particles, so when they meet and cancel each other out, their combined mass gets turned into energy. A little mass can go a long way, like turning a single sugar cube into a Hiroshima-level blast. Not a bedtime snack. You roll your eyes. Who decided this was a good sleep story again? But curiosity is louder than logic right now. You keep going. If matter and antimatter are so equal, so symmetrical, why does everything around you seem so one-sided? Where's the rest of the universe's antimatter? Shouldn't there be planets, suns, puppies made of it? That's the puzzle. You live in a world of matter. Everything from spoons to Saturn seems to be made of boring, ordinary stuff. No signs of entire galaxies made of antimatter floating out there, which makes some physicists incredibly uncomfortable because the equations predicted symmetry. A perfect one-to-one mirror. Matter and antimatter were supposed to be born at the same moment in the same amounts during the Big Bang. But instead, it's like the mirror cracked. Matter stayed. Antimatter disappeared. Some scientists still debate whether this was some early universe fluke, a cosmic coin toss, or if the laws of physics themselves leaned ever so slightly toward matter, like a rigged game of intergalactic Jenga. And that asymmetry, it's why you exist. If matter and antimatter had perfectly canceled each other out, you'd have nothing. A universe filled with light, but no atoms, no cats, no bedtime rants about physics. You shift under your blanket. Maybe that imbalance wasn't such a bad thing after all. In 1932, Carl Anderson was poking around with cosmic rays, as one does, and discovered something bizarre, a particle with the mass of an electron, but a positive charge. The first antimatter particle ever found, the positron. He didn't name it something cool like mirror electron or anti-spark, which is probably why nobody threw a parade. But it changed everything. That little discovery meant that the universe was keeping secrets. And as usual, it was doing so very, very quietly. Here's a weird side note to fall asleep to. Bananas emit antimatter. Yup. They contain potassium-40, which decays and occasionally spits out a positron, about one every 75 minutes. So technically, your midnight snack is a radioactive matter, antimatter factory. But it's still healthier than ice cream. Meanwhile, the search continued. Scientists started wondering if we have positrons. Where are the antiprotons, the antineutrons? Can we build an antihydrogen atom? Spoiler alert, we can. But it takes more money than you'd believe and a room colder than space itself. We'll get to that in a bit. For now, all you need to remember is this: for every particle you've ever known, nature has a mirror, a twin with a chip on its shoulder. And these twins don't coexist peacefully. When they meet, it's not a reunion, it's erasure. You sigh. So antimatter is real, and dangerous, and hiding. Great. But your brain won't let it go. If antimatter is the equal and opposite twin of matter, what does that say about you? The room feels quieter than it did before. The darkness suddenly feels less like an absence and more like a balance. Maybe, just maybe, the universe is made of more than it's willing to show. Your eyes are half shut now, but your brain keeps talking. It mumbles something about the beginning of everything. The Big Bang. That fiery, violent moment of creation, if you could call it a moment. You imagine it not as an explosion, but a swelling, like a hiccup in nothingness that grew and kept growing. The origin of space-time and all the ridiculous mess that followed. In that tiny fraction of a second, after the universe blinked into existence, it was hot. Like beyond stupid hot. Temperatures so high they would make the surface of the sun feel like an autumn breeze. And in that seething soup of particles, matter and antimatter were being created together. Always together. For every proton, an antiproton. For every electron, a positron. Everything came in pairs, like some divine matching game. And they annihilated each other just as quickly as they appeared. Pop, gone, pop, gone, pop, pop, gone. This was the ultimate cosmic dance, create and destroy over and over again. An endless light show performed in the darkness before the first stars were born. But then, something changed. A glitch, a misstep. A single beat skipped in the song of symmetry. Somehow, for every billion matter and antimatter pairs, there was one lonely little extra particle of matter that didn't get wiped out. 1 out of a billion. That's the only reason anything exists. That's the only reason you exist. Scientists still debate what caused that tiny imbalance. Theories range from CP violation, where charge parity symmetry breaks down at subatomic levels, to more exotic ideas like hidden particles or time-reversed reactions. Some even suggest that antimatter might behave differently under gravity, falling up instead of down. That one's still on the drawing board, but it would be wild. You picture the early universe now not as a fiery inferno, but as a storm of fireflies flashing into being, then vanishing in pairs. But 1 or 2 fireflies lingered, and those fireflies became atoms. Those atoms became stars. Then you. It's both humbling and hilarious. Your entire life, your favorite socks that text you regret sending all of it, is the leftover junk from a massive universal cancellation. And here's the weirdest part: no one knows why you were the leftover. Not you specifically, but matter in general. Why didn't antimatter win? Why isn't the universe full of anti-stars, anti-tacos, anti-you? You imagine a universe where everything is reversed, not just particles, but culture. Anti-coffee, anti-music, anti-Monday. Would they even need sleep in an antimatter universe? You hope not. That would be unfair. You reach for your water glass in the dark, half asleep, half here. There's a theory called leptogenesis. It suggests that something called leptons, particles like electrons and neutrinos, might have tipped the scales just slightly toward matter in the early universe. The math is tricky. The names are worse. But the idea is elegant. Even the tiniest unfairness in those early moments had cosmic consequences. Meanwhile, somewhere in that early chaos, photons, the particles of light, emerged. They were the byproduct of all that annihilation. Matter met antimatter and poof light. The cosmic microwave background radiation, the afterglow of the Big Bang, still buzzes through space like an ancient lullaby. And you're bathing in it. Right now. You can't see it, but it's there. A faint heat. A whisper from 13.8 billion years ago. Left behind by a universe that almost destroyed itself before it even began. That's the irony, isn't it? Antimatter might sound dangerous now, but back then it was part of a perfect system. A balance. If anything, matter was the problem. The intruder. The one that didn't know when to quit. You smirk. Typical. It's almost funny to think that the universe, this grand, sprawling cosmos with its galaxies and ice cream trucks and disappointing sequels, is the result of a tiny mistake. But that's how reality works. Imperfect symmetry. Flaws that matter, literally. A random fact floats in from nowhere. Did you know that there's a small natural nuclear reactor in Gabon, West Africa? It ran for hundreds of thousands of years, all on its own, around 2 billion years ago. The Oklo reactor, completely natural fission. And you thought your electric bill was high. It reminds you that nature loves playing with the rules of physics in secret little corners of the world. Maybe it played with antimatter too, just long enough to leave you behind. You imagine the moment when antimatter lost the battle. Maybe it wasn't even a battle. Maybe it just blinked and matter was faster. Maybe the universe didn't choose sides. Maybe it just shrugged. Either way, the leftovers became the building blocks of everything. And the antimatter, it faded, hidden, waiting. Or perhaps still whispering through the fabric of space in ways you haven't yet understood. It's strange lying here in your warm bed, breathing the air, blinking your eyelids, knowing that every cell in your body exists because something else doesn't. And somehow the silence feels a little louder now. The ceiling seems to have more depth tonight. You keep staring at it, but your mind's already somewhere else, drifting through atoms, imagining little particle dances above your pillow. You're not sure if you're dreaming or just thinking with your eyes open. Then it hits you: positrons. You have positrons in your body. Right now. No sci-fi. No alien rays. Just you, your brain, and some antimatter chilling inside your skull like it owns the place. It's all thanks to something called a PET scan, positron emission tomography. If you've ever had one, you were temporarily part antimatter. The process works like this. Doctors inject a tiny amount of radioactive tracer that emits positrons. These antiparticles don't last long. As soon as a positron meets one of your electrons, zap, annihilation. Flash of energy. A pair of gamma rays shoot off like mini flares, and special detectors use those signals to build a 3D map of your internal organs. That means the medical image of your brain was painted using tiny controlled explosions of matter and antimatter. You grimace a little. Suddenly it feels like your body's a lot more action-packed than you gave it credit for. Here's a totally unnecessary fun fact. If you got a full-body PET scan and played it back in real time, you could technically watch your brain think about watching your brain. Existential popcorn not included. So yeah, positrons are closer than you think. And despite sounding like the name of a forgotten superhero sidekick, they've become one of the most helpful tools in modern medicine. A little poetic, isn't it? The same reaction that could vaporize a spaceship can also help detect cancer. Funny old universe. But wait, if PET scans use antimatter, where do they get it? Good question, insomniac genius. The answer is particle accelerators. No, not like the one in your garage, unless you're secretly a supervillain. In which case, hey, love the lair. These are huge machines, circular or linear, that speed up particles using electromagnetic fields, then smash them into targets to create all sorts of debris, including antimatter. Some hospitals have compact accelerators designed specifically to make medical isotopes on site. It's not enough to build a bomb, but just enough to light up a brain in glowing radioactive color. And you thought your Wi-Fi router was fancy. As you drift deeper into thought, you picture the positrons moving through your body like tourists, brief glowing visitors. They arrive, say hi to an electron, and then disappear in a puff of light. No drama, no mess. Just gone. Scientists still debate whether there's a deeper symmetry at play here, one that links the quantum behaviors of matter and antimatter more tightly than we understand. Some even suspect that positrons might play a role in the mind itself, though that's mostly in the realm of speculative neurophysics, which is a very polite way of saying, weird science we're not allowed to talk about at conferences. Still, it's hard not to imagine your thoughts as tiny electrical currents zipping through the neural landscape, occasionally brushed by a visitor from the other side of existence. There's something profoundly strange about knowing that the war between matter and antimatter isn't just out there in deep space. It's happening in you, peacefully, quietly, usefully. You smirk, imagining your neurons lighting up like Vegas every time a positron explodes somewhere near your frontal lobe. Take that existential dread. But there's a serious side to all of this, too. Those positrons aren't just for fun. PET scans have helped doctors diagnose Alzheimer's tract brain tumors, measure metabolic activity, things that matter deeply to millions of people. Antimatter might be rare, expensive, and explosive, but in small doses, it saves lives. Who would have guessed that the mirror of matter would become a mirror for your own biology? The ceiling begins to blur now. Your mind, still humming, moves slower, but you can't help it. You wonder if positrons are this useful. What about their bigger cousins, antiprotons, antineutrons? What happens if you build whole atoms out of antimatter? You'll get there, you tell yourself. For now, let the thought settle in gently inside your brain. Within the curled fist of your DNA lives a secret drama. One where antimatter visits, briefly dances for a moment, and disappears, leaving behind only light. And somehow, that's comforting. Because in a universe built on violent symmetry, maybe what matters most is the flicker that lingers. You're barely moving now, but your thoughts keep digging tunnels through the darkness. You've met the positron, your little brain visitor. But what about the others? What about the heavier ghosts, the antiprotons, the antineutrons, the real bad boys of antimatter? You picture them now, floating out there like invisible sharks in a sea of particles. But the truth, they're not out there. They're in prison. Not metaphorical prison, actual containment chambers. Special ones. Ones that don't use walls or bars or burly particle guards with clipboards. These prisons are built from pure magnetic force. You imagine a lab, cold, humming, sterile, somewhere like CERN or Fermilab. In this room, there's a device called a Penning trap. Sounds harmless, right? But it's one of the most high-security facilities on the planet. Because inside it, they're holding antiprotons. Antiprotons are exactly what you'd expect, same mass as protons, but a negative charge. If they touched literally anything in the lab, they'd annihilate it. Which is why they're suspended in a magnetic bottle, levitated in a vacuum, floating like a criminal in solitary confinement. No walls, no touch, no chance to escape. It's one of those moments where science feels more like wizardry. And these machines, they're not cheap. 1 gram of antiprotons, if you could somehow produce that much, would cost hundreds of trillions of dollars. That's more than the GDP of most countries. So if anyone ever offers you a gram of antimatter at a discount, don't. Scientists are careful, beyond careful. They use magnetic fields to slow antiprotons down, cool them with lasers. Yes, laser cooling is real, and isolate them to study. Why go to all that trouble for something so violently unstable? Because the rules break down when antimatter shows up. And when physics stutters, that's when it gets interesting. One major experiment you might hear whispered about is alpha at CERN. It doesn't just trap antiprotons, it combines them with positrons to create antihydrogen. That's right, a whole atom made of antimatter. It's like building a snowman out of lava. And the craziest part? It works. Antihydrogen behaves eerily like regular hydrogen. Same mass, same structure. But when you flip its charge, strange things can happen. Scientists still debate whether antihydrogen will fall the same way in Earth's gravity, or if it might do something absurd, like fall up. That experiment is ongoing, and if it falls differently, physics textbooks everywhere may spontaneously combust from embarrassment. You turn over and mumble "fall up" seriously. Another random gem of knowledge in 1996, a team at CERN made the first antihydrogen atoms. They existed for a mere fraction of a second, just enough time to say hi, and then vanish in a puff of energy. Since then, they've gotten better. Now they can trap antihydrogen for over 15 minutes, a new record for holding a ghost in a bottle. Still, the numbers are laughably small, only a few thousand atoms at a time. Not enough to power a flashlight, let alone a warp drive. You begin to appreciate just how delicate this science is. You're talking about particles that can't touch anything, not even air, not even a speck of dust, without obliterating both themselves and the thing they touched. Imagine a wedding where touching your partner's hand sets off a fireball. That's antimatter love for you. Yet despite the danger, scientists keep pushing, because they're convinced that hidden in the behavior of these particles is a key to the universe. Maybe a better understanding of the early cosmos. Maybe a crack in the wall between standard physics and the unknown. Maybe, just maybe, a way to rewrite the rules. The alpha experiment even studies how light interacts with antihydrogen. Do these ghost atoms absorb the same colors, emit the same photons? So far, the answer is yes, which is suspiciously normal. But in physics, boring results are often hiding spectacular truths. And here's something fun to sleep on. If you built a mirror lab made entirely of antimatter, anti-floors, anti-beakers, anti-coffee mugs, and staffed it with anti-scientists running the same experiments, the laws of physics suggest they'd get identical results. Which means somewhere in some sci-fi dreamscape, there's a version of you lying in bed wondering what matter is and why it sounds so weird and dangerous. You chuckle, then yawn. In your half-dream state, you see a single antiproton floating in darkness. It's not angry. It's not evil. It's just waiting. A silent, symmetrical shadow, held in place by magnets and human hope. And maybe that's what science really is, a collection of strange little prisons we build, not to stop nature, but to talk to it. To ask questions no one else can. To listen for whispers in the vacuum. And maybe, if we're lucky, get a whisper back. You're warm, you're breathing slow, and your body's convinced it might finally drift off. But your brain, nope. It just latched onto a new thought like a terrier with a squeaky toy. Why does antimatter explode when it touches us? You blink into the dark. Sounds like a weirdly aggressive reaction. Like, imagine if someone tried to shake your hand and both of you vanished in a flash of gamma rays. Not exactly a friendly hello. But that's the reality of the universe matter. and antimatter can't share a room, not even for a second. When a particle of matter meets its antimatter twin, say an electron and a positron, they annihilate. Gone. The entire mass of both particles gets converted into energy, following Einstein's famous E(x)mc2. No leftovers, no debris, just light. A kind of clean, brilliant violence. You try to imagine it, two particles slowly drifting toward each other in the vacuum of space. No drama, no soundtrack. And then pop. Pure energy, like a silent star being born and dying in the same breath. And that's why antimatter is so terrifying. Not because it hates us, but because it matches us too perfectly. It's like that friend who knows all your weaknesses and keeps receipts. So how much energy are we talking about? Well, 1 gram of antimatter colliding with 1 gram of matter would release roughly the energy of the Hiroshima bomb. That's 1 paperclip's worth of particles, unleashing the fury of a city-leveling detonation. And yes, scientists have calculated this, because of course they have. Physics is full of people who dream in fireballs. Luckily, producing a gram of antimatter is so expensive, it makes cryptocurrency look practical. We're talking quadrillions of dollars. Antimatter is the most expensive material in the universe, not because it's rare in theory, but because it's absurdly hard to make and keep. And here's the punchline: even if you did manage to create a gram, you couldn't store it. Not in a box, not in a bottle, not in your pocket. Because the moment it touches normal matter, boom. Goodbye lab, goodbye funding, goodbye eyebrows. So what do? We store it in electromagnetic traps. Magnetic fields keep the particles suspended, levitating in vacuum like haunted marbles. They can't touch the walls, can't touch anything. It's like putting a ghost in a hamster ball made of force fields. And here's a ridiculous side note: in 2006, NASA proposed using antimatter as fuel for deep space missions. Not warp drives, not quite, but propulsion systems using antimatter-matter reactions to generate thrust. The energy density is unbeatable. Just 1 milligram of antimatter could send a probe halfway to Jupiter. But again, there's that tiny problem creating it, transporting it, not, dying. Scientists still debate whether we'll ever figure out a way to safely store large quantities of antimatter. Some dream of self-contained antimatter pods. Others say it's fantasy, like asking for a flamethrower that won't set anything on fire. Still, the appeal is undeniable. Clean energy, no radioactive waste, just particles annihilating each other into light. Elegant, final, weirdly poetic. You shift on your pillow imagining someone trying to carry a vial of antimatter through an airport. Anything to declare, yeah, just the universe's most unstable particle collection. No big deal. Here's another bit of trivia you didn't ask for. There's natural antimatter in space. Specifically, the Van Allen belts around Earth sometimes trap positrons. And near the center of the galaxy, there's evidence of large-scale antimatter annihilation happening. Scientists have detected gamma-ray emissions consistent with electron-positron collisions. So nature is already doing what we can't, storing antimatter without blowing itself up. And that's when the paranoia kicks in. What if antimatter isn't just a lab curiosity? What if it's out there in bulk, just waiting? What if there's an entire galaxy made of antimatter? Would we even know, actually? Maybe not. If a galaxy were entirely made of antimatter, anti-stars, anti-planets, anti-astronauts, it would look identical to ours. Same light, same chemistry. The only way we'd find out is if a bit of our matter drifted into their space. And then, you guessed it. Boom. Matter and antimatter don't explode because they're evil. They explode because they're too perfect. Because they balance each other so precisely, they leave no room for anything else. That's what annihilation is, not destruction, but symmetry taken to the extreme. So maybe it's not fair to think of antimatter as hostile. It's not trying to kill you. It's just trying to be you completely, perfectly, terminally. You let that thought settle in, a substance that's not evil, just incompatible. Like lactose, but with thermonuclear consequences. You chuckle quietly, eyes fluttering closed. Your whole body is made of matter. And yet your machines use antimatter to scan you. Your galaxy might share space with its opposite. And the whole cosmos rests on a coin flip that favored you just barely. Antimatter is not your enemy. It's your reflection in a mirror you can never touch. And somehow that feels beautiful. You don't even mean to stay awake anymore, but your brain's got other plans. It drifts now into the sky, past satellites and auroras, into deep space. Somewhere out there in the black velvet, your thoughts latch onto a strange, shimmering idea. What if there were stars made entirely of antimatter? You picture it. An anti-sun glowing just like ours, pumping out light and warmth across an anti-solar system. Planets orbiting it in harmony, maybe even a sleepy anti-version of yourself lying in bed wondering about your existence. Scientists call them anti-stars, and yes, they've seriously considered them. See, antimatter isn't just something we create in labs. It's also been found naturally. We've detected positrons in cosmic rays and antiprotons too, zooming through space. These particles might be born in violent events, supernovae, black hole jets, or the collisions of cosmic rays with interstellar gas. But here's the real mind-bender. What if those antimatter particles didn't just come from ordinary matter smashing around, but from actual antimatter stars? If such stars existed, they'd be virtually indistinguishable from matter stars in most ways. They'd emit the same kinds of light, obey the same laws of gravity, go supernova the same way. You couldn't just look at one through a telescope and say, ah yes, that one's made of evil starlight. You'd only know it was antimatter if something unfortunate happened, like matter drifting into its path. Even a bit of interstellar hydrogen colliding with antimatter would create a flood of gamma rays. Not the usual soft glowing starlight, but violent, unmistakable radiation. So scientists look for those signs. They scan the sky for gamma ray bursts with just the right signature annihilation. And guess what they've found? Some candidates. A few gamma ray sources seem weird, not enough to convict, just enough to suspect. The astronomical version of he was acting suspicious at the antimatter crime scene. Still, it's not proof. Scientists still debate whether these signals come from antimatter stars, or just regular stars behaving badly, maybe flaring too often, maybe burping cosmic rays. That's the frustrating part. The universe doesn't label its stuff. There are no cosmic name tags, and yet the idea refuses to die. You picture it again, a swirling spiral galaxy, mostly matter, but tucked deep in the outskirts, a rogue pocket of antimatter. Maybe left over from some early universe segregation event. Like a neighborhood that formed from antimatter clouds and stayed isolated for billions of years. As long as it doesn't touch anything, no problem. But if it does fireworks, the real issue is we just don't know. The universe is huge, and there are parts of it we'll never see, not because they're far away, but because they're moving away faster than light. The edge of the observable universe isn't the end of everything. It's just the limit of what we can ever reach. So maybe beyond that line there are antimatter galaxies, whole stretches of anticosmos just living their best symmetrical lives. Or maybe not. Maybe they were destroyed in the first second after the Big Bang. Maybe they never formed. Maybe the whole idea is a ghost born from our obsession with balance. But then again, maybe you're wrong. Physics is filled with maybes. That's what makes it sleep-resistant. It's also what makes it beautiful. For every certainty, there's a door left ajar, a soft breeze saying, "But what if?" Your bed feels distant now. You're floating in space in your mind, no pressure, no temperature, just possibility. You pass stars, nebulas, and lonely planets. And then somewhere on the edge of everything, you see a pinprick of light. A star like any other. But you know, somehow you know. That one's different. You imagine what it would be like to visit. Spoiler not great. The moment your ship's hull made of matter got close to that anti-star's atmosphere, the contact would trigger annihilation. Not just a spark, a radiant inferno. You wouldn't even have time to scream, which, if we're being honest, is pretty on brand for space travel. But the idea lingers. What if they're hiding in plain sight? What if some of the stars we've mapped in our sky are antimatter masquerading as matter? After all, we've only sampled a tiny bit of space. We've assumed that all matter behaves the same everywhere. But have we checked thoroughly? The universe is under no obligation to make sense just because we want it to. Here's a bonus fact. The AMS-02 experiment mounted on the International Space Station is actively searching for antimatter nuclei, specifically antihelium. If they find even one antihelium nucleus, it would be huge. A smoking gun. Proof that somewhere out there antimatter stars are real. So far, nothing confirmed. But the search continues. And while they search, you rest. Eyes heavy now, mind buzzing. You float there in that imagined antimatter galaxy, wondering if some mirrored version of yourself is also floating in bed, wondering about you. Thinking the same thoughts, wondering the same thing. But if you ever met, well, boom. The weight of your blanket now feels like the gravitational pull of some distant planet holding you down, just enough to keep your body still while your mind takes off again, this time to a very particular lab. Cold, quiet, buzzing with containment fields and the whispers of impossible atoms. You're back at CERN, not in the tourist part with the souvenir mugs and the Higgs boson posters. No, you're deep in the basement, in the magnetic underworld where scientists bottle ghosts. This is where they trap antimatter, not just antiprotons or positrons, but whole atoms. The real deal antihydrogen. It's a weird thought, right? A hydrogen atom is the simplest thing in the universe, just a proton and an electron, which means the antimatter version is just as simple an antiproton with a positron orbiting it. And yet this thing is ridiculously hard to make. First, you need to create antiprotons by smashing protons into a metal target at insane speeds. Then you slow them down. A lot. Then you do the same with positrons. Then you cool them with lasers and magnetic fields until they're cold enough to cooperate. Then maybe they combine and don't immediately annihilate against something nearby. It's like trying to build a snowman out of flaming gasoline droplets in a wind tunnel, blindfolded. But in 2002, they pulled it off. The Athena experiment at CERN created the first antihydrogen atoms. They existed for a tiny blink and then poof, gone. But the triumph was real, and since then the technology's only gotten better. You picture the Alpha experiment, the quiet superstar of antimatter research. This team didn't just make antihydrogen, they trapped it, held it in place using an ingenious magnetic bottle, a kind of invisible cage where the atom can't touch anything. It floats there like a pearl in a force field. For 15 minutes they held it. 15 whole minutes. In particle physics, that's practically a retirement party. They studied its properties, measured its spectral lines, the exact frequencies of light it absorbs or emits. And guess what? They were virtually identical to hydrogen. Same patterns, same energy jumps, which is boring, but in the best possible way. Because it means that antimatter really is a mirror of matter. Not just similar, perfectly symmetrical. But the game isn't over. Now they're chasing something stranger. Something that breaks that symmetry gravity. See, no one has ever measured how antimatter responds to gravity. Do antihydrogen atoms fall down? Or do they fall up? It sounds like a joke. But it's an open question. Because while every theory suggests antimatter should obey gravity like anything else, we've never confirmed it experimentally. And in science seems likely doesn't cut it. So the Alpha team launched the Alpha G project. The G stands for gravity. Physicists aren't always imaginative. They're trying to see how a single antihydrogen atom behaves when it's released in a vertical vacuum tube. Does it drop like a normal atom? Does it float? Does it fall faster, slower? The answer could either confirm that the universe plays fair, or that we've misunderstood a fundamental force all along. Some scientists still debate whether antimatter might even repel matter gravitationally. That idea's on the fringe, but hey, so was quantum mechanics at one point. Meanwhile, across the hall, there's another lab, Aegis, trying to do the same thing with a slightly different method. Science loves a little competition, even if the stakes are subatomic. You imagine a tiny antihydrogen atom suspended in a vacuum, trembling on the edge of decision. Up or down? Yes or no, gravity or mystery, and for a moment you root for it. You want it to surprise us, to break the rules just enough to crack open a new chapter of physics. Because that's the real treasure of antimatter. Not the explosions, not the sci-fi, but the questions. Antimatter refuses to be easy. It resists our instruments, our logic, our intuition. It's familiar, and yet untouchable. It makes us earn every discovery. Here's a weird side note to chew on. In 2011, scientists transported antiprotons from one part of CERN to another, just a few meters through a vacuum pipe. It was the antimatter equivalent of walking a single snowflake across the Sahara and praying it didn't melt. And they did it. That's how far we've come, moving antimatter through tubes, holding it in magnetic fields, building atoms out of it, and maybe soon dropping it. All to find out if it falls like you do. The ceiling above you doesn't answer, but the thought stays warm and gentle. Maybe somewhere in that cold lab right now, a single atom of antimatter is trembling in a trap, waiting to fall, waiting to whisper an answer that's been locked inside the universe since the very beginning. And maybe you'll be the one to understand it, eventually. But not tonight. Tonight you just rest. Your body's so still now it could almost pass for hibernating. But not your brain. Nope. It's still chewing away at the antimatter puzzle like a raccoon with a Rubik's Cube. You've learned that antimatter exists, that it's real, that it behaves mostly like regular matter. But there's one problem that keeps scratching at the back of your mind like a tiny claw. Where is it all? If matter and antimatter were created in equal amounts at the beginning of the universe, then where did the antimatter go? You picture the Big Bang again. All that noise, that soup of particles, every electron born with a positron, every proton with an antiproton. It was a perfect dance of twinning like a celestial synchronized swim team. But now you look around and all you see is matter. Buildings, planets, you. Even the annoying neighbor's lawn gnome, it's all matter. So what happened to the antimatter half of the equation? This right here is one of the biggest open mysteries in physics. Scientists still debate the details. Theories range from the conservative to the fantastical. And most of them start with a strange acronym, CP violation. CP stands for charge and parity. In simpler terms, it means that the universe might treat matter and antimatter slightly differently in terms of electric charge and spatial reflection. So maybe the laws of physics aren't perfectly symmetrical. Maybe something tilted the game board ever so slightly in matter's favor. It's like flipping a billion coins and getting one extra heads. That little imbalance, that's what we're living on. In 1964, scientists observed CP violation in decaying kaons, short-lived particles that behave differently, depending on whether they're made of matter or antimatter. It was a weird, tiny crack in the symmetry, and cracks like that are gold in physics. Later experiments with B mesons, another unstable particle, revealed more CP violation. But none of it was big enough to explain the total lack of antimatter today. So the search continued, and it still does. Some scientists propose that the universe had a phase shift early on, like water freezing into ice. During that transition, maybe one side of the symmetry won out. A matter-skewed lottery. A cosmic oops. Others go more extreme. Maybe antimatter didn't vanish. Maybe it's hiding, tucked away in distant parts of the universe, in vast antimatter-filled pockets completely isolated from matter. Galaxies of anti-stars, solar systems of anti-planets, just like ours, but backwards. It sounds wild, but again, we haven't looked everywhere. We've barely scratched the surface of space. And if antimatter galaxies are far enough away and stay isolated, there'd be no obvious signs. Until, of course, some unlucky patch of intergalactic gas wanders into the wrong neighborhood. Some even speculate that time itself might run differently for antimatter, that antiparticles might be particles moving backward in time. That one's mostly a math trick, but hey, it's a math trick that bugs a lot of serious people. It raises a deliciously absurd question. If an antiparticle is just a particle traveling backward, does that mean an anti-you is already out there watching this whole story unfold in reverse? You shake your head. That's too much. Even for now. Back on Earth, the matter-antimatter imbalance has led to a whole field of study called baryogenesis, theorizing how matter won the cosmic tug-of-war. And if physicists can figure it out, it might unlock answers not just about the early universe, but about why anything exists at all. Because without that imbalance, there would be no atoms, no gravity, no stars, no grandmothers, no saxophones, no sea turtles, no soft blankets or cold water or awkward teenage poetry. The universe would have blinked into a state of total light. Matter and antimatter gone. Just photons forever ricocheting through eternal nothing. Instead, you got lucky. There's something strangely personal about that, isn't there? You exist because something somewhere went slightly off script. A glitch. A hiccup in the laws of everything. Somewhere in all this, a random fact bubbles up when lightning strikes. It can produce antimatter, specifically positrons. Gamma rays from the bolt interact with air molecules and create brief flashes of antimatter. Nature's own weird science. So the next time you hear thunder, maybe say thanks. And then there are the really bold theories, the ones that suggest dark matter, the mysterious, invisible stuff making up most of the universe's mass, might somehow be related to antimatter. Maybe it's a kind of shadow matter that escaped annihilation. Or maybe antimatter slipped into an alternate universe, and we're stuck with the boring half. Scientists still debate that one too. You're not sure which theory feels right. They all sound impossible, and somehow all equally beautiful. But the thing that sticks with you now, lying still in the quiet dark, is the idea that you live in a leftover world, a residue. The uneven remainder after a perfect storm of symmetry wiped itself out. You are the +1 in a cosmic equation, the 1 in a billion that didn't cancel out. And maybe that's why humans are always searching, always curious, always asking why. Because deep down we know we weren't supposed to be here, but we are. And that makes all the difference. Your breath has slowed and your body's right on the edge, the tipping point between thoughts and dreams. But your mind, still stubborn, is cradling one last idea like it's a secret worth keeping awake for. What if antimatter isn't just about balance, or destruction, or mystery? What if it's connected to something even darker, dark matter, dark energy, the invisible scaffolding of the universe, the things we can't see, but that shape everything we can? Right now, scientists estimate that only about 5% of the universe is made of ordinary matter, the kind you, your dog, your couch, and your cereal are made of. The rest, roughly 27%, is dark matter stuff that doesn't emit or absorb light, but still has mass, still tugs on galaxies like an invisible puppeteer. And a staggering 68% is dark energy, whatever's causing the universe to expand faster and faster, like a cosmic balloon someone forgot to tie. So here you are, made of a substance that makes up only the tiniest sliver of everything, floating in a universe dominated by shadows. Naturally, someone asked the question, could antimatter be connected to that shadow world? It's not the most mainstream theory, but it's out there, lurking in the corners of academic journals and late-night conferences. Some physicists speculate that dark matter could be made of a type of antimatter that's somehow stable, non-annihilating. Maybe it interacts differently. Maybe it only destroys itself under special conditions. Maybe it's part of a whole second mirror world where anti-atoms form anti-galaxies bound together not by gravity alone, but by some yet undiscovered anti-force. And here's the kicker: we wouldn't see it at all. It would pass through us like a ghost through fog. No interaction, no light. Just a silent partner in the cosmic dance, always there, never visible. Even the standard model of particle physics, the most accurate and overworked framework ever devised, doesn't explain dark matter. It's like a wedding cake missing its middle layer. And antimatter might be the missing ingredient, or a clue. Some versions of supersymmetry suggest that particles have heavier, unseen superpartners. Maybe those are the dark matter candidates, and maybe antimatter interacts with them in ways we can't detect yet. You start thinking about all the cosmic rays that slam into Earth's upper atmosphere. They create particle showers, some of which include short-lived antiparticles. But sometimes, detectors pick up signals that are hard to explain, like too many positrons at certain energies. Could that be the signature of dark matter particles annihilating each other? Scientists still debate that one. The AMS-02 detector aboard the International Space Station has been watching these particles for years now. It's picked up something, but nobody's sure if it's dark matter or just some overactive pulsar in the neighborhood. That's how the dark universe works. Clues without answers, trails that vanish into fog. And then there's dark energy, which is even worse. We don't know what it is, only that it's making galaxies drift apart faster and faster over time. Some researchers wonder, could antimatter behave differently in the presence of dark energy? Could it be pushed rather than pulled? Could it be repelled by gravity in some strange twist of cosmic physics? If that turns out to be true, if antimatter falls up, then all bets are off. Then maybe dark energy is the effect, not the cause. Maybe it's the echo of an imbalance between matter and antimatter stretching across time. You're not sure how to feel about that. A little cold, a little in awe. It's strange, right? The more we learn about the universe, the more invisible it becomes. The clearer our measurements, the blurrier the answers. We build billion-dollar machines to smash particles together just to catch a glimpse of something that might not even want to be seen. You shift under the blanket and whisper to yourself, are we missing the obvious? Maybe antimatter isn't the enemy. Maybe it's not even separate. Maybe it's woven into the fabric of the dark universe like embroidery in a cloak, elegant, hidden, essential. Or maybe we're wrong about all of it. That's the thing about science, it's not about certainty. It's about doubt. Doubt that glows in the dark. Doubt that drives people to shoot satellites into space and build mile-long accelerators under Switzerland. Antimatter might be part of something bigger, something stranger. Not just the mirror of matter, but the bridge to the other 95% of everything. And that's a beautiful thought. You imagine a universe where all the invisible forces, dark matter, dark energy, antimatter, aren't separate mysteries, but parts of the same unfinished sentence. One that we're slowly, carefully, lovingly learning to read. A sentence written in annihilation, in symmetry, in shadows. And tonight, maybe just for a moment, you're part of it. At this point, you're wrapped so tightly in thought that even sleep seems like a concept from another dimension. You're floating in your own little antimatter daydream when suddenly your brain shifts direction like a cat knocking a priceless vase off the cosmic table. Wait a second. Didn't someone try to build a bomb out of this stuff? Of course they did. Humans, after all, have a proud history of turning every exciting new discovery into a terrifying what if we blew something up with it conversation. And yes, there were real attempts. Not comic book villain nonsense, real Cold War research programs buried under layers of classification where serious people with serious eyebrows asked serious questions about antimatter weapons. You imagine the conversation. So antimatter annihilates matter on contact. Yup, and releases energy, a lot of it. Cool. Can we put it in a missile? Back in the 1980s, the U.S. Department of Defense actually funded studies into antimatter-triggered fusion bombs. The idea wasn't to use antimatter as the main explosive because, let's face it, creating a bomb's worth of antimatter would bankrupt the Milky Way. No, the dream was to use a tiny amount, a few nanograms, to act as the trigger for a fusion reaction, like a nuclear spark plug. In traditional hydrogen bombs, you need a fission bomb, usually plutonium or uranium, to ignite the fusion core. But antimatter, it could do the job more cleanly, more compactly, and theoretically with no radioactive waste. That's the theory. But in reality, there were and still are enormous problems. First, antimatter is nearly impossible to produce in large amounts. Current production rates are so laughably small that if you tried to gather enough positrons to boil a cup of tea, it would take several million years and the GDP of Earth times 5. Second, storage. We can't just stick it in a thermos. You'd need a vacuum container surrounded by magnetic fields cooled close to absolute zero and protected from literally everything. A single failure, one rogue air molecule, one unstable field, and poof. Instant uncontrolled annihilation. Not ideal for a field weapon. Third, transport. No general is going to risk shipping antimatter through turbulence, or rain, or the occasional pigeon. Still, that didn't stop people from dreaming, or writing white papers, or proposing future satellites powered by tiny antimatter reactors. Because if you could solve all the logistical nightmares, antimatter offers an absurdly high energy density, 90 megajoules per microgram. That's millions of times more energetic than TNT. Sci-fi writers loved this. In Star Trek, the Enterprise runs on a matter-antimatter reactor. In Angels and Demons, remember that the Vatican is almost blown sky-high by a stolen antimatter bomb stolen from CERN, which, if you're wondering, caused real public confusion at the time. CERN had to issue press releases to assure people they weren't stockpiling weaponized antimatter under the Alps. You smile. It's kind of funny. Antimatter, for all its drama, might be the worst weapon ever created. Too expensive to make. Too volatile to move. Too impossible to store. A diva among explosives. Scientists still debate whether there's any realistic future for antimatter propulsion or weaponry. But increasingly, they've turned their attention to more practical things: medical imaging, particle research, gravitational experiments. The dream of antimatter as a silver bullet has faded, which is kind of beautiful in itself. Here's a weird, oddly wholesome fact: the largest use of antimatter in the world today, not weapons, not spaceships, not doomsday devices. It's hospitals. Yup, PET scans using positrons are saving lives every day. Antimatter is helping doctors find tumors, map brain disorders, and diagnose heart disease. So while governments were dreaming of explosions, scientists quietly made healing the dominant use case. Somewhere the universe is slow clapping. But let's not pretend antimatter isn't still dangerous. If you dropped a single antihydrogen atom on a surface, it would annihilate. It just wouldn't do much damage. Like flicking a spark into a bathtub. Spectacular, but not destructive. And to date, no military has successfully created an antimatter weapon. No satellite is running on antimatter engines. No missile carries a positron payload. It's still theoretical, still out of reach, which is probably for the best, because maybe the universe knew what it was doing when it made antimatter rare. Maybe it was protecting us from ourselves, giving us just enough to learn, but not enough to destroy. You feel that thought settle over you like a second blanket. Antimatter isn't some doomsday powder. It's not the villain in a cape. It's delicate, fleeting, almost gentle in how it refuses to linger. And the real power isn't in what it destroys, it's in what it reveals. Balance, symmetry, the fine edge between being and not being. You close your eyes. Somewhere in a lab, a positron meets an electron, a flash of light, nothing more. And that somehow feels like peace. You've stopped fighting sleep. You're just letting it hover now like antimatter in a magnetic trap, so close to drifting off, but still suspended, still thinking, still curious. And now your brain does what it always does in the final stretch of exhaustion. It turns to the movies. Because let's be honest, your first real exposure to antimatter wasn't a textbook or a research paper. It was fiction. Maybe Star Trek. Maybe Angels and Demons. Maybe some low-budget film where someone in a lab coat shouted, "If that antimatter touches anything, we're all doomed." The dramatics are questionable. In most of pop culture, antimatter is portrayed as a kind of magical space plasma, glowing, pulsing, wildly unstable. A power source for warp drives. A weapon of last resort. A glowing orb of ultimate doom. You chuckle. It's not like real antimatter glows, or pulses, or hums ominously. In reality, it's invisible, silent, sterile. There is no color, no noise, no dramatic light show. When matter and antimatter meet, there's no boom like in the movies. It's a precise mathematical interaction. Annihilation into gamma rays. Clean, efficient, quiet. So, where did the myth come from? Probably from the idea that anything this powerful must also be flashy. Take Star Trek, for example. The USS Enterprise uses a matter-antimatter reactor to power faster-than-light travel. In this imaginary tech, particles of antimatter are stored in magnetic bottles, then injected into a chamber where they collide with matter to create energy. The process sounds legit, and in a way it is. The underlying physics is sound. The engineering, however, is science fiction. Because again, we can't even store antimatter for more than minutes without extreme precision. And we're making about 1 billionth of a gram per year. So no, you can't fill your gas tank with it. Not yet. In Angels and Demons, the stolen antimatter bomb is said to contain 1/4 gram of positrons, enough to level Vatican City. You'll be happy to know storing that much positron in a single capsule would require containment fields so powerful they'd collapse under their own contradictions. Also, no hospital in the world has that much antimatter. Even CERN, the real-life lab depicted in the film, couldn't produce it in 1,000 years. Still, fiction has its place. Because even when it gets the details wrong, it gets one thing right: antimatter feels profound. It's the perfect symbol for duality. Matter and antimatter, light and shadow, existence and erasure. That's why it shows up so often in sci-fi. Because it speaks to something primal. The idea that everything has a mirror and that meeting your mirror is dangerous. Sometimes the symbolism is the science, but not all media gets it totally wrong. In fact, a few science communicators, YouTube channels, documentaries, even animated explainers have done a brilliant job translating antimatter into something people can understand without a degree in particle physics. They explain it with apples and bowling balls, with magnets and billiards, with cartoons and metaphors. All tools in service of one goal: to make the universe less scary and more real. And that's a worthy cause. Because let's face it, if the only thing people know about antimatter is that it blows things up, we've missed an opportunity. Antimatter isn't just explosive, it's elegant. It's the universe holding up a mirror and asking, do you see what's missing? Here's an odd little fact to drift off with. In 2005, a team of researchers proposed that certain types of black holes might spit out antimatter as they evaporate. These hypothetical particles could zip through space and eventually be detected on Earth. They haven't been yet. But it's one of those sci-fi sounding ideas that's actually scientific. Science fiction at its best does exactly that. It gives science permission to dream bigger. And so do you. Lying there curled up in your blanket, eyes half-lidded mind, floating just above the edge of dream, you think, maybe we need fiction. Not just to explain the universe, but to feel it, to imagine it, to wonder. Because sure, the physics is precise, but curiosity, that's messy, beautifully, hopelessly messy. It doesn't care if antimatter explodes, it just wants to know what happens next. So the next time you see antimatter on a screen, glowing like radioactive jello, don't roll your eyes too hard. Smile a little. Because even in its fiction, it's trying to reach you, to remind you that there are still mysteries, still mirrors, still ghosts made of energy and symmetry floating just out of sight. And whether you're in a lab, or lying under the stars, or just falling asleep, that's a lovely thing to remember. By now your muscles have softened into the mattress. You're weightless in your own bed. But your thoughts, they've pulled you back again, away from movies and explosions, and into something far more personal. Antimatter is helping people. Every day. This is the unexpected part of the story. Because after all the talk of annihilation and cosmic asymmetry and secret anti-stars, you'd think antimatter was just a ticking time bomb waiting to misbehave. But in quiet hospital rooms under fluorescent lights and the whir of machines, antimatter is doing something else entirely. It's healing. You return to positrons now, not theoretical ones, not the ones zipping around in cosmic rays, but the ones being used in PET scans, that's positron emission tomography. If your memory's a little fuzzy after midnight, here's how it works. Doctors inject a tiny amount of radioactive tracer into your body, usually something like fluorodeoxyglucose, which is just a glucose molecule tagged with a positron-emitting isotope. That molecule behaves like normal sugar. Your body doesn't know the difference, so it goes where sugar would go into metabolically active tissues, like the brain or a growing tumor. Then the tracer decays. A positron is emitted. It flies a tiny distance, just millimeters before meeting its counterpart, an electron. And right there inside you, they annihilate. The result, 2 photons, gamma rays. They shoot off in opposite directions, and a ring of detectors around you catches them. Using timing and angle, a 3D image is built layer by layer, cell by cell. You're being mapped by annihilation, diagnosed by vanishing. The irony is not lost on you, antimatter. The very substance feared as a cosmic eraser is saving lives by making the invisible visible. Doctors can spot tiny tumors, catch disease early, measure brain activity, even track how certain parts of the body respond to treatment over time. And all of it depends on the moment 2 particles decide to disappear together. Here's a strange, beautiful fact. Most of the positrons created in PT scans don't make it far. They annihilate within a few millimeters of being born. They are the shortest-lived heroes in medicine. And unlike MRI or CT PET doesn't show structure, it shows function. It's like eavesdropping on your body's whisper-level conversations. You let that image settle in, your body glowing with tiny fireworks. Silent messages turned into light. Scientists reading those messages like star maps. Now take it a step further. Researchers are working on therapeutic uses of antimatter too, not just imaging. The idea: inject antiprotons into tumors. Let them burrow deep, and when they annihilate, the energy they release could destroy cancerous cells with precision. It's still experimental, still in its early stages. But the dream is real, a kind of targeted radiation therapy driven by matter-antimatter interaction with minimal damage to healthy tissue. Antimatter as medicine. You imagine a future where hospitals have their own tiny accelerators, where positrons are made on demand, where a diagnosis isn't a fear sentence but a roadmap to healing. All thanks to particles that vanish as soon as they arrive. You smirk again. Bet that didn't make it into the sci-fi movies. There's something oddly comforting about this part of the story. It reminds you that the universe doesn't deal in good or evil, just in balance. Antimatter isn't bad. It's just rare. And when we treat it with care, it responds with clarity. Even in annihilation, there is knowledge. You yawn. Let your eyes close. Let yourself imagine one last image, a glowing body on a PET scan monitor. Colors blooming in the shape of lungs, a heart, a brain. Not fear, not chaos, just light. Data, hope. Antimatter helping someone sleep better tonight. And maybe that someone is you. At this point, your thoughts feel less like steps and more like slides, smooth, effortless, drifting between reality and something softer. And as the scientific side of you rests, the imagination side stretches its legs. You ask the question no textbook ever dared to entertain. What if the universe had flipped the coin the other way? What if antimatter had won? You picture it, an entire cosmos made not of protons, but antiprotons. Not of electrons, but positrons. Hydrogen replaced with antihydrogen atoms built in reverse stars fueled by mirror reactions. And somewhere out there on a planet that never formed from matter, there's a city made of anti-brick and anti-glass. Maybe someone's drinking anti-coffee from an anti-mug, annoyed at the anti-traffic. Could it exist? Yes. In theory, absolutely. Antimatter behaves the same as matter in almost every way. Gravity pulls it down. Electromagnetism governs how it bonds. Chemistry happens just as it does here, only with flipped charges. Antioxygen still binds to antihydrogen. Anti-people could still breathe, though. Technically, they'd be breathing anti-air. You chuckle softly. You imagine brushing your teeth in an antimatter universe and the toothpaste tastes like oranges because, well, why not? Who's to say the flavors wouldn't flip too? But here's the strange grounding part: no one would know the difference. If the whole universe were antimatter, it would look identical to this one. Physics would unfold in exactly the same way. Stars would burn, planets would orbit, life could emerge. And unless you dropped in a single grain of ordinary matter, which would immediately explode, you'd have no clue you weren't in your original matter-based universe. Scientists call this CPT symmetry, a concept where if you flip charge parity and time, the laws of physics still hold. So if you reversed every particle into its antiparticle, mirrored the spatial configuration, and ran the clock backward, you'd end up with something that still surprisingly works. It's a thought experiment that makes your head hurt just enough to stay awake another few minutes. You roll over. In your mind, this antimatter universe takes shape. Cities grow. Beings evolve. Maybe they look like us. Maybe not. Maybe they're clouds of floating consciousness or jellyfish made of plasma. But they think. They wonder. They build particle accelerators. And maybe, just maybe, they ask the same question in reverse. What happened to the matter they lie awake on anti-pillows, staring at anti-ceilings, wondering if somewhere far beyond their own galaxies, there's a strange, impossible world made of opposite stuff. And maybe, like you, they know they'll never reach it, because matter and antimatter can't mix, not for long. Their meeting would be beautiful, and instantly final. You sigh. There's something bittersweet about that. These two halves of the universe, so alike, so perfectly matched forever, divided by the very perfection of their symmetry. You imagine shaking hands with your anti-self, a warm grip, a familiar smile, and then nothing. Just a bloom of light, an echo. But what an incredible moment that would be. It makes you think about identity in a quiet way. What makes you you isn't the particles, it's the patterns they form, the way they move and think and remember. And in theory, antimatter could do the same. So maybe in some abstract cosmic poetry, antimatter could be you, could become you, given the same laws, the same environment, the same possibilities. Maybe it already did. Maybe you're the shadow version, and the universe just flipped the coin before you ever knew the other side existed. That idea doesn't scare you. It calms you. Because if reality could have gone either way, and you'd still be here thinking, dreaming, breathing, then maybe this whole existence isn't as fragile as it feels. Maybe it's written deeper, in pattern, in symmetry, in something beyond the particles themselves. You blink slowly, the ceiling just a blur now, your body heavy, your thoughts finally slowing. Antimatter isn't the villain, it's the possibility. The alternate story the universe chose not to tell. And yet in every PET scan, every cosmic ray, every flicker of annihilation, it whispers that it was almost here, that it almost won, that it still exists, mirrored, silent, waiting. And tonight, as you drift off in a universe made of matter, you carry with you the echo of what might have been. You're teetering on the edge of sleep now, your body heavy and relaxed, but your mind, that stubborn creature, won't quite let go. It circles back to one last stubborn mystery. Why does antimatter break the rules? More specifically, why does it break symmetry? You've heard the phrase CP violation before, the cosmic cheat code that lets matter win. But even that's only part of the story. There's another symmetry called CPT symmetry, which combines charge C parity P and time reversal T. Theoretically, physics should be perfectly symmetrical if you flip all three at once. It's a sacred rule. Yet antimatter flirts with breaking parts of it. Physicists have found that sometimes antimatter behaves just a tiny bit differently from matter not enough to break the universe, but enough to cause ripples. Why, no one knows. Scientists still debate whether this tiny asymmetry in antimatter is the key to why you're sitting there alive, while your antimatter twin is nowhere to be found. Some think it might involve neutrinos, ghostly particles that rarely interact with anything. Neutrinos themselves might have subtle differences in behavior between matter and antimatter versions. If true, these tiny quirks could have tipped the cosmic scales during the universe's first moments. Others suggest new, undiscovered physics beyond the standard model. Particles or forces we haven't even dreamed of yet. Imagine that a universe with hidden laws waiting to be uncovered by the next generation of scientists. One recent experiment called BASE at CERN tested the magnetic properties of the antiproton and compared them to the proton. So far, they match almost perfectly, but even the smallest difference would be a revolution. You lie still, contemplating. Antimatter in all its mysterious glory is not just a mirror image of matter. It's a riddle wrapped in symmetry, wrapped in an equation we haven't fully solved. And that uncertainty, it's what makes the universe so wonderfully strange. Here's an odd little fact. Some physicists believe antimatter might even help explain why time moves forward. Why you remember the past, but not the future. It's called the arrow of time, and antimatter might hold clues to its directionality. As you feel your eyes close further, you realize that antimatter is less a villain or a ghost, and more a question. An open-ended invitation. A whisper from the universe saying, "You don't know yet, but keep looking." And you will. Because that's what makes you human. Curious. Restless. Unwilling to settle. You exhale slowly. The room grows quieter. The night deepens. And antimatter, forever elusive, forever balancing, waits patiently for the next question. Your breathing softens. Your heartbeat slows. You're almost there on the edge between awake and the quiet world of dreams. But before you slip away completely, your mind lingers on a final thought experiment. What if right now an entire person made of antimatter stood beside you? Not some shadow or ghost, but a real breathing, thinking anti-you. The same shape, the same laugh, the same awkward smile, only every particle in their body is flipped. Every proton replaced with an antiproton, every electron with a positron. Would you be friends, strangers, enemies? You imagine the moment you reach out to shake their hand. There's a beat of hesitation. Then the inevitable, instant annihilation. The universe flickers and pulses. A tiny bloom of light, a flash that says you met not you, and both vanished in a whisper. But what if you didn't touch? What if antimatter versions of ourselves could exist parallel to us, but never intersecting worlds side by side, invisible to one another, separated by the thin veil of annihilation? Some theories suggest that antimatter might be traveling backward in time, or living in mirror universes where the arrow of time runs opposite. Maybe the anti-you is already out there looking at a mirror image of this very moment, wondering about their existence just as you are. The thought blurs now, soft and distant. Antimatter is not just particles, it's possibility, a reflection on the cosmos's edges, the balance between being and not being, the fine line where physics folds into philosophy. As you settle deeper into sleep, you let the thought dissolve like mist. There's peace in the symmetry, comfort in the mystery, because in the end, you and antimatter are tied by the same cosmic dance, two halves of a whole forever intertwined, yet forever apart. And somewhere in the quiet night, annihilation hums a lullaby. You smile and finally you rest. So now here you are, still soft somewhere between sleep and silence. We began tonight by staring at the ceiling and wondering why the word antimatter feels so heavy, so unfamiliar, and yet so close. And as we walked slowly together through the shadows of particle physics, we found that antimatter isn't some dark sci-fi villain lurking on the edge of science. It's something far more honest, more symmetrical, more poetic. We learned that every particle has a twin, that matter and antimatter were born together in the heat of the Big Bang, only for antimatter to mysteriously vanish or hide. We explored the brilliant ghost flashes inside your own body during a PET scan and followed antimatter all the way into magnetically trapped prisons in underground labs. We traced the whisper of anti-stars chased gamma rays across the sky, and even imagined worlds made entirely of antimatter, flipped but familiar. We peered into the darkest corners of the cosmos and asked whether antimatter might hold secrets to dark matter, or even time itself. But most of all, we realized this antimatter is not destruction. It is balance. It is the mirror the universe holds up to remind us of what could have been. And that reminder, gentle, luminous, eternal, is why you're here. Listening, dreaming, curious. So tonight, as the weight of the blankets deepens and the questions grow softer, let yourself drift. Not with answers, but with wonder. Because some of the most beautiful truths aren't meant to be solved, just followed like starlight on the ocean. The antimatter isn't gone. It's just out of reach. And that's exactly where it belongs. End of script. Good night.